So today's lesson will be about the arithmetic or the numerical side of vectors. Now yesterday we saw the geometrical side of vectors, how we can add and subtract and scalar multiply via graphing. And while that's a good skill to have, it's sort of annoying. Um, I don't want to draw a Cartesian plane every single time I want to add or subtract vectors. So today is all about the mathy side, the written side of vectors. Let's recap. Oh, actually, I guess we should start with the lesson goals. So the lesson goals for today is we should be able to add or subtract vectors analytically, or I'll just say algebraically. Yesterday we did it geometrically, today we'll do it algebraically. And today we're also going to be able to find the components of any vector given its magnitude and direction. So yesterday we did find the components of a vector, but we sort of did it geometrically, the terminal point minus the initial point. Today we're going to see an alternative way to find the components algebraically. So the first thing I want to do is sort of recap the important topics that we covered yesterday. So some important ideas. A vector is defined. Actually, let's give it a name. A vector U is defined by its magnitude, and the notation we use is absolute value bars, and its direction, and the notation we use is theta. What other important thing did we talk about? We talked about, terminal points. If U has initial point x sub 1 comma y sub 1 and terminal point x sub 2 comma y sub 2, its horizontal component, which I'll call just as a plain old regular x, is x sub 2 minus x sub 1. It's the difference in the x's, but you always have to do terminal minus initial. And its vertical component, y equals, is going to be y sub 2 minus y sub 1. It's always the terminal minus the initial. And then we talked about the geometric way of adding and subtracting fractions. So to add and subtract fractions, jeez, it's been a long day. To add and subtract vectors. To add and subtract vectors, geometrically, you start one vector where the other ends. The resulting, or the resultant, vector is from the initial to the overall final point. And for example, say we had vector, I'm going to add up a whole bunch of vectors. So, just randomly, so let's call that vector A. Clearly it starts down here and it ends up here. So if I want to add to vector A, I have to start at this point here. So let's say I added vector B, and I'm going to go crazy, and C is all the way over here. Ooh, that's not a straight line. C is all the way over here. And let's say D is somewhere down there. So you can go as crazy, complicated, as many vectors as you want, but you start at the original initial and you end at the overall terminal. That is the resulting vector. So this blue here is A plus B plus C plus D. So to add and subtract vectors geometrically, it's sort of like follow the leader. You just connect the chain links. So today what we want to do, another important thing is notation components. So vectors in component form may be represented by, and let's stick with vector u. You can do this pointy bracket notation. You can do this I plus j notation. Or you can do this stacked column notation. Now, the reason why we typically talk about vectors in component form rather than its default magnitude and direction is because component form makes math simple on us. Because it's easier to work with purely horizontal and purely vertical components than it is with angled numbers, because purely horizontal and purely vertical, that's our default normal system. That is one-dimensional math. So it transforms a two-dimensional quantity into one-dimensional quantity, which is the math we've been doing since, kindergarten all the way through Algebra 2. So let's talk about the ideas. So um, let's talk about adding and subtracting vectors in component form. So you can see how component form reduces the mathematics to very, very simple operations. Right? So suppose we had two vectors. I'll do u and v. Those are the standard vectors. So let's say vector u had, in component form. I'm going to use angled bracket notation. You can use whatever notation you want. It's going to be the same concept. What letter should we use? Should we use x and y's, x sub 1, y sub 1? Or u sub, I'll do this. I'll do u sub x, u sub y. I think that's very easy to understand. Oh, u sub x, that's the x of the u. And suppose vector v has components v sub x, v sub y. Now, word of advice, if your handwriting is not as great as mine, u's and v's look the same. You guys can use a's and b's if you want in your notes, or notice how my u's always have a tail on them. So this u has a tail, and my v's will not. So I will never write u's just like this, because that looks so much like a v. When I do vectors, my u's will always have a tail on it. Right. So suppose I have these two vectors, u and v. Well, here's how easy it is to add and subtract vectors. Then, how do we add vectors in component form? You just do the math on their components. So what's u plus v? Well, that's the x component of u plus the x component of v, comma, the y component of u plus the y component of v. That's it. If it's already in component form, if to add vectors, you just add the components. Same thing with subtracting. How do you subtract two vectors when you have it in component form? You just subtract their components. The u of the x minus the v of the x, and it goes in order. U minus v, u goes first, v goes second. U of the y minus v of the y. Right. I guess I could just keep going on and on and on, but I think you guys get the idea. The properties of vectors follow the normal arithmetic properties of numbers. So the associative property, the commutative property, all of that still applies. So let's talk about scalar multiplication. If c is any real number, then suppose you had scalar multiplication of a vector in component form, you just distribute that number c into the component. So that's c times the x component, comma, c times the y component. Right? There are loads of other properties of vectors. I'm not going to bother writing them down because, again, you should already know it. U plus V is the same thing as V plus U. It's commutative. Vector addition is associative. Vector uh, has an identity. If you add a zero, you get the same thing. So it's all. I'm not going to bother writing it all down. It's pretty self-explanatory. So for example, let's just do some quick examples here. So let's say I tell you that, EX, so these might be the things you'll see in your practice. If vector U is, say, -2, 5, and vector V is, say, 2, -8, find, you know, U plus V. Well, that's easy. Let's color code these. Just for the notes, I'll color code them so you can see what's going on. So that's blue, yellow, whatever this color is, red or pink, and whatever this color is, purple, -8. So to do U plus V, just add the x's. So that's -2 plus 2, comma, and add the y's. 5 plus, I think I use this color, -8. That's it. That's all you really have to do. So you can see why algebraically we love component forms. It makes vectors easy. 0, -3. Otherwise, what you would have needed to do is you need to draw this guy out, tack on this guy out, and again, so -2, 5, that's something like that. And then 2, -8 is something like that. And then you would have gotten that resultant vector. So instead of having to draw it out, break out some graph paper, we were able to get the answer algebraically, pretty simply. Now, it doesn't matter how complex things look. It works. It utilizes the same, algebraic concept. So I can do like 3u minus, I don't know, just make this up, 4v. So it's the same concept, except you got to subtract, and you have some scalar multiplication going on. So let's go ahead and just write it out. So I'm writing it out a lot more than you need to, just for the purpose of the notes. So I'm going to do straight up substitution. So that's 3 or 3 parentheses u. So what is my u here? That is -2, 5 minus 4 times v. What was v? 2, -8. So then scalar multiplication is just regular distribution. So that is -6, 15. So you have a choice here. You can distribute the -4, or you can leave the negative and distribute the 4. If you just utilize the 4, the negative needs to stay there. If you're distributing a -4, the minus turns into a plus. Your choice. For my notes, I'm going to distribute the -4. So I'm going to change that to a plus, and then distribute the -4. -8, positive 32. So then it just becomes like the above problem. You add the x's. So -6 plus -8 is -14, comma, you add the y's. 15 plus 32, what's that? 47. There you go. Right. So adding, subtracting becomes child's play. Adding, subtracting vectors becomes child play once you have component form. So the other lesson goal that I expect you guys to be able to do is to be able to be comfortable going back and forth between component form and the magnitude and direction of a vector. And it's going to be funny. You're going to, when we do this, when you find the formulas, you're going to realize, geez, all of these look the same. We've done this before. So let's talk about converting, or let's say the relationship between magnitude and direction the relationship between magnitude and direction with component form. Right. That looks complicated. So that's just the title here. All right, so suppose we had a vector u with magnitude absolute value. Actually, let's put this on one line. With this being the magnitude, theta is the direction, x is the horizontal component, y is the vertical component. Right. So let's draw this out. So let's draw a random vector, u. So boom, there's vector u. We know it has a set magnitude, and we know it has a set direction. Now, direction without a coordinate grid is hard to draw, although yesterday we said that vectors do not need coordinate grids. There's no law against it, so let's put this vector u in a coordinate grid. And let's make our life easy on ourselves and by putting the origin at the initial point. So we know that this vector has some direction theta, and we should know it has components. The components visually look something like this. Here's your x component. Here's your y component. And we want to find the relationship between the black label, magnitude and theta, and the blue label, the horizontal vertical component x and y. Gee, haven't we done this already? Haven't we drawn this picture 1,000 times? We already have a relationship. So that's sort of the big spoiler. To go back and forth between component form and the regular format, magnitude and direction, it's what we've been doing all over and over and over in Unit 8. It's not, we don't call it polar form and rectangular form, but it is analogous to converting back and forth between polar form and rectangular form. So I mean, yes, these are, quote, new formulas to put on your index card, but it's really the same concepts. So we can just see that ... The x component is just magnitude cosine theta. The y component is magnitude sine theta, right? Gee, doesn't that sound familiar? Oops, you can't see that. X is r cosine theta. Y is r sine theta. The only difference is instead of calling it r for radius, we use the notation for magnitude. And then on the flip side, we can see that the magnitude is the square root of x squared plus y squared. It's the same formula we wrote, although in Unit 8 we did the squared version without the square root. For some reason, when it comes to magnitudes and vectors, we always take the square root version, whilst for polar coordinates and complex numbers, we use the squared version. Weird, don't ask me why. And then we can see that the relationship between the direction and the components is tangent. Tangent of theta is y over x. And you have to be careful when you find the direction. You always have to be mindful of what quadrant you're in. So, I mean, I hope I really don't have to do any examples here. But I guess for the sake of completeness, let's go ahead and do a couple of examples. But you guys should be experts at this after doing Unit 8. So example, find the components of a vector with length, remember the word length means magnitude, length 8, and direction of pi thirds radians. Just to make the labeling easier, let's give this vector a name. So find the components of, say, vector u with length 8 and direction of pi thirds. All right, so let's do this. So to find the components, I need to find x and y. Gee, according to the idea, x equals r cosine theta, or magnitude cosine theta. Y equals magnitude sine theta. And what do you know? They give you all of the pieces, right? So it's just a plug and chug problem. So x equals 8 cosine of pi thirds, y equals 8 sine of pi thirds. And since these are special unit circle angles, I expect you to be able to do this without a calculator. So cosine of pi thirds is 1/2, so that's a 4. That's radical 3 over 2, so that's 4 rad 3. So there we go. There are the components. So let's write vector u in component form. And I'll leave this up to you. You can write it in whatever notation you want. If you can do, or depending what the instructions say. So if you want to do the square bracket, the pointy bracket notation, that's 4 comma 4 rad 3. If they want the i's and j's notations, that's 4i plus 4 radical 3j. Or if they want the column, or you could put in the column notation, 4 rad 3. Yep, your choice. And then, I mean, I hope I don't need to. Well, let's just go ahead and do it for the sake of the completeness of the notes. The other direction, find the magnitude and direction of a vector u, which has components, I don't know, 2 comma negative 3. Just right off the bat, I know that 2 and negative 3 are not special values, so we're most likely going to have to use a calculator here. So let me go ahead and grab a calculator really quickly to be prepared. Alrighty. Alright, so the magnitude, again, it's just a straightforward formula. It's Pythagorean identity, or Pythagorean theorem. So it's x squared plus y squared. So that's 4 and 9. What's that? Is that 13? Boom, there we go. And then we have tangent of theta equals y over x. So the reference angle here, so again, 3 over 2 is not special. So I'm going to deal with reference angles. So I'm going to ignore the negative. I'm going to, in my calculator, in radians, I'm going to do inverse tangent of 3 over 2. So that gives me a reference angle of about 0.983 radians. So now I have to place them in the right quadrant. You can see our original component is positive x, negative y. So that's going to be in the fourth quadrant. So here's my direction, 0.983 radians. Now with vectors, we almost always use positive angles. So I know some of you guys are used to doing the smaller negative angle, which mathematically is not wrong. It's just with vectors, we typically only use positive angles. So this angle here would be the 2 pi minus the reference. So if I go ahead and do 2 pi minus that, I get approximately 5.3. Oh, nice. Approximately 5.300. So there we go. There's the magnitude and direction. So the magnitude, again, is radical 13. The direction is about 5.300 radians. So it literally is the same stuff we've been doing 8.3, but in the context of vectors rather than coordinates or polar form or complex numbers. So give it a shot. Apply what you learned in Unit 8 to this new thing called vectors.